All right. Well, I think we're probably at a place where we can get started. First off, thanks everyone for joining us today for Dojo 5 Lunch Learn. We've been doing a series of these for the past month, and we're going to keep on kind of doing fun and interesting topics in embedded. And so if you have any ideas on topics that you'd like to hear about, topics you'd like us to talk about, feel free to bring those up with us. Otherwise, if there's any questions that you have during the presentation, feel free to add those to the chat, and I'll attempt to get to them as we're discussing. And if I miss something, I'll definitely leave time at the end so that we can talk through them. But today we are talking about AI, specifically on the nRF52840. This is a chip that we at Dojo 5 have used quite a bit, and so I'm really excited because AI is just getting to the point where we can start using it on what we call edge devices, or like deep embedded devices, 8-bit, 32-bit, 16-bit type of micros. So it's been pretty neat. Real quick on me, my name's Joe, from a family of 5, and former John Deere, now leading Dojo 5 and focused on firmware excellence. As I mentioned before, we're just kind of do everything with firmware and really trying to modernize it. I really modern firmware. I'm passionate about building great cultures and high-performing teams. There's my awesome family. And then Dojo 5, just quick introduction, embedded experts out to modernize firmware. Dojo 5 comes from Dojo being a place for immersive learning. And that's what we do with our clients hand in hand as we build kind of the latest, greatest bleeding edge modern firmware devices. And then the 5 is basically a foundation and family. So we focus on rich engagements with our clients and making everybody feel like a big part of the team, as well as internally as well as externally. Product and services company based in St. Paul. So what is embedded for this talk? When we talk about embedded for the purposes of this talk, we're really talking about a computing device with a dedicated function, generally bare metal or RTOS, less than 100 megahertz, less than a mega flash, less than 512K of RAM. So specifically, AI and libraries like TensorFlow or others have been available on higher class devices like Linux class devices for a couple of years, but really it's been pretty bleeding edge, and it still is pretty bleeding edge to be able to do that at the edge, at these at the scale of these devices where they're where they have very little RAM. They're not even running Linux. They're running some kind of like bare metal type of, and oftentimes they're battery powered. So it's really like the question is, can we do this in a battery powered environment that where we can still last, weeks, months, or even years? And the answer is starting to become yes, which is pretty exciting. Just kind of for scale, if you're not familiar with type of wattage and what kind of power do these typical embedded systems take? Well, like an AC unit in your house would take 1,000, 2,000 watts. Laptop charger is 80 to 100. Raspberry Pi is a 5-watt device, which is still quite a bit of juice. Roku's 3.5, little TV connected device, or a smartwatch. Now we're getting down to the milliwatts. And really, what I'm planning on talking about here is that there's a library from TensorFlow called TensorFlow Lite, and they've been running that on kind of Android or iOS class devices or Linux class devices for a while, but they're now targeting these edge devices, which are now in the milliwatt or even sub milliwatt. When you average it out over time, it might be a sleepy device that's waking up infrequently and needs to make a measurement, does something, and in the case of AI, why you might be applying it is maybe you've got a really difficult signal processing type of application, and it's hard to write an algorithm for it. And then you apply AI to do those kinds of things. And I'll just say that embedded development is just tragically behind, and the mobile and web guys have all of these cool mature unit testing tools, amazing debuggers, one-click DevOps, real-time monitoring, all this stuff, quick and reliable deployment. all stuff that Dojo 5 is trying to bring to the table. But the cool, what I like is or what this is all about is about AI and how that is now finally coming to our screens, and we're able to bring the value that AI can bring to our users and our clients. It's really exciting to see some of the applications that are coming up really quickly. So yes, TensorFlow Lite for micros, as I kind of alluded to before, has finally kind of started to bridge the gap for microcontrollers. There are a couple other options out there for getting AI and machine learning in general onto microcontrollers, but they have a pretty smooth flow that I'm going to kind of walk through today and show off a couple different applications. TensorFlow Lite for micros was born out of Google, and really it actually started as TensorFlow Lite, which I mentioned before, and really what they needed is the wake word detection. They were getting all of these, they're seeing the Google Home and Amazon and Alexa and all that are all kind of woken up by these wake words, and they needed this to run with very little battery power in the background all the time. And so one of the things they like to talk about with TensorFlow Lite is, hey, this is already running on billions of devices of Android phones. It's not like an experiment that may or may not see the light of day. This is already providing value in the world on billions of devices. So it's pretty battle tested. Pete Warden, Raziel are two guys that kind of helped move that forward. And then it was open sourced in March of 2019. So it's kind of like a StealthWorks project internal to Google for a little while. And then 2019, it finally opened it up to the world. And like I mentioned, targeted at less than 1 milliwatt devices. So this really is like typically devices that have a sensor or two, and they're fairly sleepy, and they're just kind of sitting there doing something, kind of like chewing on it. I think there's just a really interesting number of applications, and it may seem limiting at first, and like we're not talking about like devices here that are going to be doing video processing, 100% of the time. I think there are a lot of innovations that could be done there as well in terms of doing sleepy devices that could take an image and then run some heuristics on it or run some neural networks on it and then determine something about it. But something that's like full video, like car driving and stuff, like they're using large GPUs and many watts of power to power those devices. To make that work. So it's like an interesting new class, and what's great about it is that's exactly where Dojo 5 plays. So in order to make this work for micros, they did kind of hamper or kind of limit TensorFlow API to a subset of like the full TensorFlow library. But I think you'll find that there's still a large number of applications that fit into this, and we'll go through a couple of them today. So when you're putting together a deep learning workflow, these are typically the steps that you go through. You decide on a goal, collect a data set, design a model architecture, train the model, convert the model, run inference, and then evaluate and troubleshoot. And so I think in step 0 that I don't have listed here too is like decide if you really need AI. And this isn't necessarily a talk about like where AI applies or not, but I'll just say that like the advice I give people is like, if AI is cool and trendy and fun, and it does unlock a really huge potential of some new applications, but there are definitely situations where it doesn't make sense. If there is a pretty good algorithm that you can run, you're going to have a lot more predictability and spend a lot less time, building something that runs that algorithm rather than trying to work it into a neural network. We'll go through a couple of these today, but there are some tricks in order to make the neural networks work quickly and efficiently on microcontrollers that you have to make sure that you're aware of too. And sometimes it just doesn't make sense. But then you decide on a goal. You got to decide what is our neural network going to be computing? Is it going to be something where we're classifying devices? Or some kind of like sensor data? Is it, predictive analytics on industrial machines is something that is getting a lot of attention now. And so like, am I measuring some kind of sound coming off of a, squeaky bearing or something on an industrial machine? Or Am I measuring temperature fluctuations on a particular factory device or something in your factory line? Or there's a lot of different opportunities there. And so you decide on your goal. What is that? You know, let's just say it's listen to a squeaky bearing sound and decide if the device is going to fail. You know, if your factory line is going to go down, and try to predict that ahead of time. So then you have to collect a data set, and it's not insignificant the amount of data you need to collect to make these neural nets work. They need to see a lot of data, not just background. You know, they need to be trained in kind of all the different situations that they might see. So it could be, you know, if in our squeaky bearing situation, you might want to collect, you know, a functioning, you know, bearing. You might want to collect data of just the background noise without the machine running at all. You might want to collect the sound of a squeaky bearing when people are talking near it. You know, factory workers are having a conversation. You also need to collect, you know, squeaky bearing when they're not having a conversation. Maybe there's a horn or a buzzer for shift change, you know, collecting that. So there's kind of like a lot of different, you know, situations that you need to think about if like, for instance, your sensor is a microphone. And it needs to be trained in all those situations in order to really kind of be able to differentiate between the different situations that you're trying to train it for. So you design a model architecture. This is really the black art of AI machine learning right now. There are basically a number of structures that people have found are good for certain types of applications and certain types of neurons that you put in there. And I guess the way I always typically approach is I look for other people that have solved something similar to what I've done, and you use that as a starting point, and then you continue to refine it as you want to improve your model. So I've got a little bit of a screenshot over there of just like, you've always got an input layer, and then you've got some number of hidden layers, and then you've got an output layer. And so it's really those layers in the middle, and how you connect them and how many of them that is kind of what you tweak, and it kind of is just trial and error at the moment, you know. But I would recommend starting with you know, finding someone who's done something similar, and then starting with a model that they've found to be successful, and then tweak it from there for your application. They're typically, this is where the you know, where a lot of the research goes into this right now. Then training the model. So you have to collect a large data set, and then you train the model. And in one case, like a classification type of model, you label your training data. Some of it will be, you know, like machine, you know, squeaky bearing, and other ones will be not squeaky bearing. and so you group those together. We'll see this again as well a little later, but you try to train these models so that they with enough data so that they're going to learn. There is I think such a thing as too much data, and you can overfit the model where it becomes so in tune to the data that you provide it that it kind of fails in situations that weren't exactly like the data that it saw. And so there is a little bit of fine tuning there as well to get the model to predict well, but not overfit the model. And then you convert the model, and that's really the new step when you're doing TensorFlow Lite for micros. And this really, the model that you'll get at the end of step 4 is a TensorFlow model, but we need to convert it to a TensorFlow Lite model. And that conversion you'll see happens pretty smoothly. At that point, the model is really a huge array of weights for the neurons, and represents the structure of the neural network as well as all the weights that are there. So converting the model basically boils it down to something that TensorFlow Lite for micros can run. And there's also an opportunity here to make the neural network more efficient for micros as well. We'll talk about ways to do that. Then you run inference, and that's really the magic. You ask TensorFlow Lite to run inference on a data set. It goes into the input layer, runs through the weights, and pops out the other side, and you have some predictions on what the neural network thinks has happened. And then you evaluate and troubleshoot whatever you need to do. You know, is it working well? Is it not working well? Does the model appear to be overfit? Does the model appear to be underfit? or maybe you're successful. The hardware I'm going to use today is this Arduino Nano 33 BLE Sense. So it uses a uBlocks module, and inside of this uBlocks module is the nRF52840, which is a really nice chip. We've been using the nRF52. They've actually come out now with an nRF53 just in the last couple of months that has a little more, it's kind of their next gen nRF52. So I definitely look at that if you're thinking of designing this into something, or you just want to play with a newer generation. But the 52840 is going to be around for a decade, I'm sure, and it's a workhorse. It does BLE. It's a Cortex M4, as I mentioned, with 64 megahertz mega flash. And you can get these things for under $5. Or the Nordic chips. If you're doing enough quantity, even closer to $2. So you can start to see that, like, if that's, and that's the whole CPU, the oscillator, everything. So it's like all you need to add to that really is a battery and a sensor, and now you've got something that's pretty darn cheap, and it can be running AI in the field and doing something with that data that's valuable to yourself or customers. So I would just say, if you're looking to play with this, it's a great platform, because not only is that chip really good, but it's hooked into the Arduino guys have put some time into machine learning that we're going to show off today, as well as there are some other folks that are building on this platform as well. So it's like a good place to get started and get your feet wet. If you get it, make sure you get the Sense version. They have a version of this board that's exactly the same, but a lot of the sensors are depopulated, and so that really limits what you can do with this. I've had people accidentally buy the wrong one, so make sure you get the Sense version. It's about $35, so it's again really easy to get started on it. As I mentioned, Arduino support was ported by Sandeep Mistry, who is like a superstar in the especially BLE, but also a lot of other just like embedded stuff floating around there. And he has like go check out his GitHub. He's got a lot of stuff going on. And Dominic, in October 2019, so fairly recently, lowered the entry point significantly for getting into this and starting to play around. And they've got Arduino setup instructions here too. If in the announcement blog, you can check out these slides after the talk. All right, so now I want to get into a demo and just kind of show off what are we talking about here with AI, and how does this work. We're going to start with what I call a hello world for AI, and a number of folks do use this as kind of a hello world for, like, is my AI system working? And so what we're going to do is try to build an AI system that can predict a sine wave. And so, if you're familiar with the sine wave, of course, there's an X value and that, you feed the X value into the sine function, and out comes a Y value. And so we're going to see if we can train a model that will be able to predict the sine. So it's not actually like calculating sine, it's predicting it or inferring it through the model. If you've done any AI before, a lot of work, a tool that most people use is IPython notebooks or Jupyter notebooks that are running Python backend. So, and this is one that the TensorFlow guys have set up that kind of helps us. And it basically, it's like almost like a wiki, but you can execute the pieces of the wiki. And so it's really pretty nice and easy to kind of walk through what this does here, and we'll just where is it? So okay, so this is running Python, and each of these blocks can run a set of Python code. So this is just kind of setting us up, and then when I hit run, it runs that code. And then it will provide any output that code provided. In this case, this is just kind of setting us up. We're just importing the operating system and setting up some details. Then we need to set up our environment, which is basically installing TensorFlow 2. And so these are all, and hopefully this is making sense, but these are all commands that you could either run in your Python environment locally, or you could just grab this Python notebook and run it here now. Oh, neat. No wonder if something changed with the requirements recently. Neat. Well, it'd be a little hard to, we can walk through this, unfortunately. Well, we'll see. I don't know if everything got installed that needed to, but we'll keep on walking through and we'll see. All right, so we're gonna know, because if TensorFlow didn't get installed, then NumPy didn't get installed, and we're gonna know pretty quick here. Import NumPy. So NumPy is just a mathematical tool that gets used fairly frequently to calculate, do all kinds of mathematical calculations in Python. And obviously bringing in TensorFlow and setting some kind of random seed. Keras is TensorFlow's high-level API for deep learning. If you've done any TensorFlow stuff, then you've probably seen that before. All right, so now we're ready to get our sine wave. So we're going to generate what is our training set, really. We're going to train the model, or we're going to build our data set that we're going to use to train the model. So we're grabbing basically a random uniform sampling of a real sine wave, and then we are shuffling those random values to guarantee they're not in order, because we don't want the model to learn, something tricky about if every next value is always less than or greater than. We want it to kind of be able to, given any x value, predict what the y value is. And then we're just plotting it to show, hey, we've got a random sampling of, the sine wave. And if we were to zoom in on that, each of those little blue marks is actually a separate kind of circle or dot that's been matched to the sine wave. Now, it's important in some of this to add some noise. What would happen is if we didn't have the noise, our model could very easily get overfit to the actual sine wave. And so we want to add this, and again, just to kind of help us predict from real world data. You can get an overfit, and also this example is not as realistic if we had like super clean data. So let's make it a little messy. Okay, and then what you typically do after this, now we've got some data, you split your data. You need a training set, you need a validation set, and you need a testing set. And this 60-20-20 is often a typical kind of breakdown. So 60% of the data goes into training. It is really it's really important for your model to have a lot of training data to be able to correctly run this type of stuff. Validation is used during the training to verify, to basically test how well trained the model has become. And then testing is after that. Basically, so it actually uses the validation data as it's going, and then testing data at the end is something that we can use to independently verify the accuracy of the model. So you can see they're splitting up the samples, and now we've got basically, and they're randomly all over the place in the sine wave, right? So we've got the blue dots are training data, the red dots are testing data, and the gold dots are validation data. So we've got like a random smattering, all across the sine wave for those. All right, so now it's time to build the model, and in this case, we're gonna define 2 layers. You notice here, even they don't really just explain how they did that, but in this case, it's pretty simple prediction. So like the architecture of the model isn't too terribly important, and we can get a fairly good result. But this is where some of the magic happens, and where you go learn, pick a model that maybe somebody else has used for the type of application that you're coming into. But here they're just using a simple model architecture called a sequential model, and they're adding a couple layers to it, 8 neurons. And then a final layer that has a single output value, which is going to be what do we think the sine result is, right? And then they compile it, and they're just using kind of standard stuff. And once we've got that, we've got our network, and now we need to train it. And this is where training just basically runs it, and it always trains it like many, many times, and is kind of annealing. It's slowly moving the weights around and kind of perturbing different weights to try to get the best. It's searching and trying to optimize the model for the best weights in the amount of time that we give it. So in this case, we're giving it 500 epochs. And we can run that, and you can see it runs fairly fast, but it can take some time. This is where, like, if you're doing anything more complicated than a sine wave, you could spend easily tens of thousands of epochs training your model. And this is where people spend a lot of money on like cloud services, big GPUs in the cloud that can compute this stuff more quickly to speed up their ability to train their models. You can spend days training models. And especially when you get into video, those models can take a while. And so often the solution right now is to throw money at it and to make it train faster. But yeah, and this is where a lot of silicon manufacturers actually are starting to build in, either build application specific hardware accelerators to train these models more quickly, even in the cloud or locally on-prem. Or even GPUs that are optimized for running the models. So there's a lot of computation happening here. But at the end, you can see this loss value is, well, we're getting lower. You can see that it trended over time. We were pretty much trained out of the gate. I guess, by this loss number, basically you want this probably it's a measure of how good your model is. And so the lower it gets, the better your model is. You can see the first couple of iterations, we really made significant progress on the loss, down in the 30s, down in the 20s, and then down in the teens. And that's kind of where we got diminishing returns. By epoch 250 already, we're pretty much as trained as we're going to get. And then validation loss is measured in the same thing against the validation data. So, and then, and here we can even see, here's the training data loss and validation loss. So here they're kind of graphing it over time. So you can see that the model, it gets trained, and then once it's trained, there's nothing much more to do. Let me update that with our data, which looks largely the same. It kind of happens the same way. And here we can even see with getting rid of the first few epochs where it was really making a lot of progress. Here we can see that it's pretty much trained after 200. So and we can see the loss basically. It's a decent model, right? Now, what they're walking us through now is being able to just kind of make it a little better. Now, because then when we look at it, we're thinking like, okay, so it's about 16% wrong, and you can see it's come up with a very simplified version of sine wave, and this isn't terrible, right? I mean, you can look at this and say like, oh, well, I can see like if I map an x value to a y value, I'm not that far off from sine wave, but obviously this isn't quite what we were looking for. We were looking for something a little bit better than that. And so what that's telling us, and again, this is a little bit of the art and science of doing this, is that, hey, I need a more dense neural network, like an 8 neuron network with 2 layers just was not enough to really capture a sine wave. So that's what we do next. We create another model, model 2, and this guy has 16 neurons. But largely using the rest of the model the same. We'll train this new model with some new neurons, and you can see now our loss is starting to get down to 9.865%. Now it's like, okay, that clearly was something that helped us a lot. Now we're down even to 1% loss, and it's kind of just fidgeting there at about 1. So this looks like it's going to be much better for us, right? And then in epoch 16, we're way down at 1%. So great. And then drawing a graph of that, we can compare. And this is, it took longer to train, which is usually a good sign too. And the loss is, much better once we get down, because we just we're tapped out the neurons with only 8. And there we go. So then when we do this, we've got a much better graph. Now we're kind of what we wanted to do, right? With 16 neurons, we're able to predict sine wave pretty well. All right, so now we've got a model and we've got it trained. The next step is let's generate a TensorFlow Lite model. There is a TensorFlow Lite converter which converts the model basically into a giant array that you can pull in, and that TensorFlow for micros knows how to grab. There's a little bit of different information. And then one thing that I alluded to is knowing how to quantize the data, or knowing how to make the model run more efficiently. So TensorFlow Lite out of the box uses floats for everything. And on big beefy computers, that's no big deal. On little tiny micros where you want to get things moving quickly, sometimes that can be a big deal, not only from a CPU standpoint, but also from a memory standpoint, because they take up more space. So in a lot of cases, what we found is that quantizing the model can actually get you almost as good a results without having to while being able to save both in speed and efficiency. All right, so here we're converting it from a Keras model. We're taking model 2, which is our one that actually trained pretty well, and we're converting it with the TensorFlow Lite converter. And then we're opening it, and then we're reshaping it, and we're using their built-ins int8, which is basically telling it to quantize it to a 8-bit integers rather than floats, which seems like it could be a big deal, right? We're losing a lot of data there, right? But in fact, here we can compare the model sizes, and you'll see that like the original model is 2736, the quantized model is 2500. Not a ton of data now, but we'll see in the next demo that actually for a little more complicated model, there's a lot of difference here, and it can make a big difference. We want to test the quantized model, so there's no quant. We have both the no quant and the quantized one, and we see that the Lite predictions are the X's, the Lite quantized predictions are the green X's, and actually it's a little hard to see on that graph, but the green X's are pretty much bang on where the blue X's are. So it's really done a good job here, and this is part of the magic that's been brought to the industry in the last probably year is being able to do this and make it really appropriate for micros now. The other thing we didn't see here, but would have seen, is that inference is taking a lot less time to run, or will take a lot less time to run on a micro on the quantized model than to run in float. So it translates to better battery life. Here we're installing just a tool called XXD that helps us format this into a format that a microcontroller can take. And then we have the deploy to microcontroller step. So now if I cat out that model, here is the binary representation of the model, the trained model to predict sine wave. And there it is. We got a big chunk of data, and we've got the length of the model, 2512, is just what our model takes up in memory. So 2.5K. So let's get into, let's try it on a real device here. So I've got Arduino set up here, and what we've got here is the Hello World application. So in the setup instructions that I have linked in the slides, it'll get you to this point where you can set it up. Once you've got Arduino installed and you've got the TensorFlow Lite stuff set up, you'll see that you get an Arduino TensorFlow Lite item under the examples. And then you can choose from these examples. We're using the Hello World example. And it's pretty informative if you're not familiar with TensorFlow or TensorFlow Lite to kind of walk through what does the Hello World main function look like. And of course, in Arduino world, you've got a setup and a loop function. But you can see that in our loop, we're going to be basically walking through the X values one by one. So this is just kind of like calculating the X value. And then multiplying that times the total range, and then here's where we've got the input data that we're providing. So we provide that in X data to our TensorFlow model, and then we invoke the interpreter, which really runs our inference. And then if it ran okay, then it runs okay. And there's a handle output handler here that TensorFlow uses. And when basically we have an X value and then the predicted Y value that came from inference. And when what it does is we use that Y value to calculate a brightness, and then we write that out to the LED. So the idea is if we've done this correctly, and we're getting a nice sine wave predicted, then we should see the LED kind of like nicely dimming, and there should be no jumps or spikes in the brightness. We should see a nice kind of like sine wave of brightness flowing through. And so the way that we toss in our sine wave data is right here. So they've got it. There's got the sine model data CPP file here, and here's some old data that they brought in. I want to use our data though, and you can see it is different. Data line attribute. I mean, well, besides they've named them differently, so we have to kind of hack this up. You can see like there's, you know, the first byte is 18, you know, and then some zeros, and then a 54, 46. Some of it's the same, some of it's different, but it is a different model that we've calculated independently, you know, during this talk. So let's pull that in. And then as you can see, we're going to have to rename it gsine model data. Here, I'm just going to pull that in. All right. So, and then we're going to rename the length there. And we're going to rename the name of the model to be this. We'll make sure it's data aligned, although that probably doesn't matter in this case. And they also have a const just to confuse people. All right. This one might need to be const too. I bet it does. All right. So let's see if we can build this. Now, while I'm building that, I'll just kind of show off. Here's what the BLE Sense board looks like. You got it from the picture too, and it just connects up over USB, and that's your ability to connect here. Oh yes, and we missed a const somewhere. Let's see, conflicting data origin. Yeah, maybe this isn't supposed to be const. We'll throw it at the wall one time, and if that doesn't work, then we'll have to just dig in real quick to the header file. Okay, extern const, what do they want? Oh, they want extern const int. Unsigned int. And what do they want? Previous extern const int, unsigned int versus just int. Oh, I see. So they want just a constant. All right. So as we build this, and there are some warnings that pop out, and that's kind of par for the course on some of this. All right, so now we've got our sketch. Uses about 17% of the Nordic's 1 mega flash. So hey, we've got a lot of room for other things. It's not doing anything too terribly complicated, but that's still pretty neat, I think. Okay, so now if we'll just double check that under tools that we've got the right board selected. Here's our Arduino Nano 33BLE selected. And we can upload that sketch. And then what we'll see once that uploads is that this LED that's kind of bright green now will start pulsing. There it goes. It's pushing the code. All right. So actually, I'm sorry, it's this orange LED. So if you see that orange LED now, we can see that it's pulsing. So we are running AI on this device right now, and it is running, you know, in milliwatts. So it is, it's pretty amazing. All right, so let's do something a little more complicated. Back to the slides, quick. That kind of shows the flow of how you'd go through. There's a company that I ran across, and actually one of the guys who was initially involved in TensorFlow Lite for micros as co-founded this company called Edge Impulse, and they just provide a nice web-based tool that walks you through TensorFlow Lite for micros. I'm not affiliated with them in any way. I just think they have some nice tutorials. It's unclear exactly what their business model is yet. I think they're just trying to kind of get users and get people interested in TensorFlow, and specifically TensorFlow on micros. And the BLE Sense board is kind of like a first-class citizen on their site. So with COVID and everything going on, I thought something interesting would be like a cough detection unit. So you could imagine one of these devices for, I don't know, 10 bucks, 15 bucks could be mounted, you know, maybe in a waiting area, quarantine area, or maybe just like, you know, waiting area for a restaurant, waiting area for a school or something, and it could detect coughs. And then that might give like an alert to somebody that, hey, there's, you know, somebody might be sick around here, just go check it out, you know, see what's going on. And so I thought, okay, well, this is something that we might be able to do with AI, and these guys have a microphone on them. So I walked through a tutorial that Edge Impulse has. Now they do some different stuff, but they're in their case, they're talking about detecting whether the water's running or not. So another really interesting type of application, you know, did the wheel leave the water on? Could I build this into a faucet, you know, where it alerts me, you know, over BLE if I left the faucet on? I thought the cough stuff was cool too. But it kind of walks you through a whole model, and I'll bring up the model. I'll say that the longest part of doing this was getting cough data in, because it needs a lot of cough data. And at this point, I've only collected about 5 minutes, and this was basically 2.5 minutes of me coughing, which is more painful than it maybe sounds, and then 2.5 minutes of different varies of silence. And I did things like coughing while I was typing on the keyboard, or coughing while there's a little bit of background noise, you know, and also, you know, just background noise and no coughing. So, and so how this works is they have a integration, or they have a way to connect your device remotely. I won't show it here, but when the device is connected remotely, this little ball shows up green, and it just allows you to collect data with this actual device using the actual microphone that is going to be on the device, which I think is really cool. They've got a little script that you run in the background, and and this guy just runs a little application that knows how to kind of wait for the command to start recording, and then it records stuff to his local memory, and then it ships it up to the cloud, which is pretty slick. And then once you've got your devices set up, then you can start collecting data. And so yeah, when I've got the sensor board connected with that script in the background, it'll show up here. You can start sampling, you can record a bunch of audio data. Here you can see I've got a lot of some background and some coughs, and this is what we call a classification problem in machine learning. So we're trying to decide, given an audio sample, was it a cough or was it just background noise? And so I created 2 labels. One is coughs, one is background. And then I created a bunch of audio samples, and I labeled them. Some of them are background, some of them are cough. And that's what we're going to use as our training set, and as well as our test data, and as well as our validation data. So it splits this training set. So pretty slick flow there. And then impulse design. So in this case, I'm using a processing block called MFCC that is used pretty commonly as a neural network for audio processing. And this is just the case where, like, I didn't invent MFCC, you know, some other folks did, and they did a lot of work to figure out what is the right neural structure model architecture for an audio problem, an audio classification problem. So that's why we're pulling that in. They also do some slick things with time series data, the window size. So what they're doing is that I gave it a 10-second window of audio, and they're slicing it up into 1-second chunks, and then running the neural network and the training on those chunks, and then having them overlap by 500 milliseconds. So you're really trying to squeeze out as much learning as you can from the same data set. You'll see like an image training types. A lot of times you'll give it one image, then you'll say this is a dog, and then you'll flip it 180 and say this is also a dog, and you'll flip it upside down and say this is also a dog, because you're trying to train the network. No matter what orientation of this dog you get, it can still find it. So the same thing is happening here in audio, where they're trying to squeeze out extra information from the training set. And then we're using kind of a really basic neural network classifier. And then we got output features, which is basically just, it's going to tell us, is it a background or is it a cough? I've already saved this impulse. There are, in here, they do allow you to change this, change a number of settings that, to be honest, there's more here than I have dug into. But there are a lot of options and opportunities here to tweak. And you can see here's some of our neural network settings. So like if we think we might need 1,000 training cycles, and what's our minimum confidence rating? Like when we're predicting this, what do we want it to think of as, like, we need to know it's a cough. And of course, some of these numbers depend on your application too. If it's not, if you'd rather have false positives than false negatives, then you would adjust your minimum confidence rating accordingly. There, you'll see that in here, our input layer has 637 features. Then we've got 30 neurons, 10 neurons. There's a flattened layer. So there's quite a lot. It's a larger type of model, but we can, we can change this however we want. We could add 40 here just to see, what's going to happen here, right? And then we could start training. And then they actually do walk us, help us walk through the training process, and we don't have to set it up. And now we can see, very familiar to what we were seeing in the example, that here's our loss is slowly going down. We're to 50%, which isn't particularly good, and now we're getting a little better. And then our accuracy is going up accordingly. So it does take a little time. As I mentioned here, we've got a slightly more complicated one, and we bumped it up to 1,000 epochs, or it's probably about a minute to train this model, but you can see that we are still, seeing some pretty good improvements in accuracy, and it's still training and getting better and better every time. So just while that's training, there is a opportunity to retrain models. There's some live classification ability on this as well, so that we can, if it turns out that we don't like the way our model was trained, we can try to make it better. Let's see. So while that's working, retrain models with known parameters. You can train the model. There's live classification, which basically, it's in process training, but this training. And then, then they've got model testing and then deployment. We'll be able to see those once the training is complete. But and basically the rest of this demo is deploying this out of Edge Impulse and then pulling it onto the device and then doing it. So this would be a good time for questions, if we got any questions, and we can and toss those into the chat if you've got any. I think we've got, yeah. So I guess one of the questions I see is, how would you do this with a smaller micro device? I guess is kind of the answer. Hey, can I do this with like a cell operated device? And I think, or a coin cell device. And I guess I'd say, yep, definitely you can do this with coin cell operated devices. I think that it all depends on your application and how you want to. Yeah, what's allowable in your application. If you're able to kind of be sleepy for a while and just wake up every once in a while, or even in this cough detection case, like if you're able to kind of like wake up on some kind of loud sound, and then you could be asleep overnight when nobody's in the waiting area, and then wake up when there's a loud sound, start recording right away, and then run inference on that 5 seconds of audio or 10 seconds of audio, then boom, you're going to have a pretty good ability to detect coughs versus no coughs. So it's I think it's going to be really it's just exciting to see all of the applications that are there, but you can definitely do that with low cost. And then another one, I guess, about medical stuff. So yeah, I think on medical devices is interesting because they FDA gets involved, and there's been a couple instances of machine learning being used on a medical device, mostly as service in the cloud, or software as a service type of things, where it's like a radiology type of stuff where it can determine maybe what's going on more quickly and sometimes more effectively than a radiologist could. And so I think that's been really exciting too, is seeing the FDA take that on, but you do have to kind of think through that. I think there's a ton of, there's this whole regulatory piece, I guess, that's very, very new. That definitely I would get some help with if that's an application that you're going for. But beyond that, if you are thinking about some interesting medical applications, I think there are a ton of them out there where we're going to see devices in the next 10, 20 years able to, slowly start diagnosing issues, maybe in very specific cases, and then handing off to doctor for, verification there. But yeah, it's been, there's some really interesting things happening in that space. So. And I kind of threw in some numbers here on the training. And interestingly enough, we're getting extremely low losses, but our validation loss is actually going up. And so that what that means is we probably have overtrained the model. So we'll see how well it operates. But yeah, the validation losses went up from about, it looked like we were down at 46 and we've slowly been ticking up. So we'll see how well this model works. It's always kind of fun to kind of play with this. Like I mentioned, if we wanted to retrain the model, we could here. We could try live classification. If I basically gave them one of these, I can basically, so on the cloud without having to run it on the device, I can give it a classifying I think this is one of me coughing. And so what we can see then here is that, it's not finding coughs. It thinks it's background, thinks it's background. And then right at 1500, it's like, oh, dude, for sure that is a cough, right at 1.5 to 2.5 seconds. And then he's like, yeah, this is a cough. So we can kind of see that there's like, this has correctly detected that, hey, right at this stage, there's definitely a cough there. So seems like it's working all right. And then, yeah, the deployment step is pretty quick and easy. As I mentioned, these guys have made the Arduino Nano kind of like a first-class citizen, so you can actually export it. And here's where the optimizations come in too. So this allows us to compare the innate quantized to the float, similar to what we did in the Python script. They actually do an estimate as well of like how long inference is going to take on one versus the other. You can see in the example that's behind here, it's like 19 milliseconds for the quantized model and 220 milliseconds. So that's like a pretty huge difference, the order of magnitude difference on how long it takes to run. And you can see the size as well as RAM usage is almost half with a quantized model. So once you get more complicated models, it really can make a pretty big difference to do the quantization. No, I'm not sure why that failed there, but okay. See if we can get through it. Any other questions? All right, not seeing any. Anyone doing anything cool with AI, or have any thoughts about what they might be doing, looking to do AI? Let's touch something in the chat, and then maybe I can share it with the rest of the folks. Well, it looks like Edge Impulse is having a little bit of trouble. I'm gonna zip back to the yeah. But anyway, they spit out this really nice model, or a really nice basically a zip file that you can import into Arduino. It pops up under yeah, here we go, cough demoing, and then you can go grab the microphone example here, and it will it'll run, and then you can actually run it. Here, let me run it on here, and we can see what it looks like when it runs. Does take some time to compile sometimes. Yeah, I don't know. Edge Impulse must be having a little trouble. But oh, there we go. It's still doing something. But yeah, the other thing I guess I'd say is that yeah, can we have AI and tiny microprocessors? Just kind of wrap it up. And yeah, the answer is yes. And I hope I've inspired you to do something great with AI. There's these tools are pretty easy to use. Once you get to real world applications, there's often a lot of details. I would say, if you're interested in anything that Dojo 5 has to offer, we've done this before on a couple of micros, and would love to do to help you out or somebody you know. Even if you're just interested from a hobbyist perspective, we love to hear from folks like that. We're on Twitter and LinkedIn, and happy to have interesting conversations about just what people are playing around with as well, because we love to hobby and tinker too. So any of those levels. Another thing I'll mention is Dojo 5, as I mentioned, is modernizing the embedded workflow. We've got we do a lot with continuous integration and continuous deployment and helping folks automate their build systems. And one of the big pushes that we're into right now is getting AI and machine learning. When you can see what Edge Impulse has done kind of in their website, where they kind of walk you through the flow of building that. But then imagine as you're building a device and trying to maintain it, doing that over and over again through development and then deploying it to customers and stuff. That piece of the puzzle is largely, there aren't a lot of solutions for that. We've got a solution, so we build and customize that for folks. So if that's something you're interested in too, or even just general automation, build automation and stuff for embedded, that's what we're focused on. So, and with that, let's see, yeah, there's some references here. So we are inferring now. So we should be able to show off. There we go. So now it's trying to decide if it's a background or a cough. So it knew that was background. Oh, it incorrectly classified as cough there. But if I do like a cough, then there we go. So that was 92% cough. So we might need to crank up our numbers a little bit. I do think we overfit the model a little bit here, but it's pretty good at figuring out that, hey, that's background. This is indeterminate. If we said we need over an 80%, cough to say it's a cough, then great. So, yep. There we go, 90% cough. So as long as we pick up, it looks like our background, it's a little confused maybe, but when we get a cough, it can definitely find a cough. So there we go, we've done it. Thanks so much for joining me, appreciate it. and stay in touch.